Hello and welcome to the AP Physics 1 review video on work, energy, and power. Today we want to talk about some ideas that deal with the ideas of work, energy, and power and what that means. Work, energy, and power are different than some of the things that we've looked at before because now we can look at a system, rather not just one object but multiple parts of things going on. We use two big ideas. Either one, if we have a case where the total energy in the system is equal to the final, right? Final E is equal to initial. Or we could say that if there's external work done on a system, there's a change in energy. What does that really mean? If we don't have any outside forces on something, energy is conserved. If we have external forces such as friction or we lose energy to the system, we have work done. Work, as we define as force times cosine angle times displacement. That's our first big equation that we're going to use in a bunch of stuff. We've got gravitational potential energy is mg delta y. So this is gravitational potential, mg, change in height. Kinetic energy, 1/2 mv squared. You notice that the speed or moving energy, kinetic energy, is based on mass and velocity. Stored spring energy or spring potential energy is 1/2 kx squared. Now in this, k is what we call the spring constant. That's basically dependent on each spring that we're looking at. And x is not displacement. X is the amount of squish or amount of expansion of that spring. And we also, in this unit, we've introduced something called Hooke's law. F is equal to kx. Now let's talk about what these ideas mean. Now in dealing with work, energy, and power, we can deal with the system. So if we have something and someone was to go ahead and jump off a platform and dive into the water below, even if they jump off and they do this, or if they fall straight down or just kind of plop, we don't really care. One thing we want to say is work, energy, and power. Energy is a scalar, which means no direction. Energy is something that things have, so we don't care about the direction of things that are going on. So in each one of these cases, as long as this person doesn't run off, right, we're talking about having the same amount of energy. What does it mean? The initial amount of energy is equal to the final amount of energy. In this case, this person standing up here could have some types. Could have gravitational potential, they could have kinetic, they could have spring, and at the bottom, they give any of those forms. Now you should realize at the top, as long as they don't run, that goes away. At the bottom, there's no more change in height. This goes away. And the idea of just mentioning springs here is silly. That goes away as well. So what does that mean? So we could use this mg delta y.
Excuse the interruption. Again, bus 66 has just pulled in. Please allow those students in your classroom and adjust your attendance. Again, bus 66 is just unloading now.
Notice I wrote mg delta y for the initial gravitational potential. It's equal to 1/2 mv squared because that's the only velocity that I have left, the only energy that I have left there. And you can see how we could write this. Notice divide by m, mass falls out. I can do some fancy stuff here. 2g delta y. Just 2g delta y. Root of this is equal to. So in that case, we just went ahead and we found our final velocity at the bottom, right? 2g. Right? Now notice, we don't care if they fall this way, whatever, because energy is scalar. We don't care about the path taken. Now, other things you want to look at with this is, yes, energy, we have it conserved. It's always conserved. But if we're talking about mechanical energy, moving or potential energy, that's when we start saying to ourselves, okay, what do we need to look at? If we have a case that something is moving and sliding this way, let's say it's sliding to the right, okay? So it covers some displacement in that direction. That means that there's a force present. If we're saying it's sliding and there's a frictional force that way, it's going to be going that way. So what does that mean? That means energy is removed from that system. That means that there's work done on that object. So really this case is I'm pushing something, I let it go, it's sliding, but going to come to a stop. What can we do? Well, we've got this idea that work is our change in energy. Now if you say to yourself, okay, what does that mean? I've got like a million equations in this unit, I've got a million relationships to look at what's going on. Well, in this case, it went, you see, so all of our potential, all of our types of energy that we had at the beginning at the end minus what we start with, right? Okay, I know that looks a little bit sloppy, but I'm saying all of our finals minus all of our initials. Notice in this case, it has some, well, hold on. It doesn't have any kinetic at the end. If I'm saying it's coming to a stop, doesn't have this, doesn't have this. Well, hold on. It had some kinetic. All of that stuff simplifies to negative K naught. Well, how does that make sense? How, if energy is, it doesn't have direction, how can we have negative? Well, it's the transfer of energy, right? So if this is a negative energy, that means that energy is lost. Now, if this thing was moving and then stopped, that would make sense. It's going to lose some energy. In terms of our work stuff, F cosine theta d. Now, in this case, remember, theta is the angle between force and displacement. If they're like this, that means our angle is 0. They're not like this now. Our force that we're looking at is this way. Our displacement's this way. Our angle between the two is indeed 180. So F cosine 180 times my distance. You should realize the cosine of 180 is negative 1. Well, hey, guess what? I just got negative 1 there. So F d negative, negatives fall out. So you agree in this that I can find force, and this can be rewritten as 1/2 mv squared. I could use this to find like mu. Does that make sense? Like to find the coefficient of friction, or to find the average force in those things, or to find the distance that this thing would cover. So notice I'm just setting this thing up to say, like, you could use the ideas of change energy to look at this. You could also look at this in terms of a fall and saying, okay, what if the final energy didn't equal the initial? What would happen? There'd have to be work involved. We also dealt with the ideas of spring stuff, okay? Dealing with spring stuff, if I have something that's on a spring like this, please note that that's our equilibrium position. If we stretch it out, this here to here, that is indeed our x value. Or stored spring energy, right? You notice that it's going to take twice the force in order to lift something, but it means it's going to have 4 times the energy because that's an exponential term. Okay. Other useful ideas that go along with this are, if we look at a force distance graph, and we find that it does something like this. The area underneath here is equal to the work. And we know work is the change energy. So with that being said, if you knew some ideas, you could use the area underneath to find the new speed. How so? Work is change energy. If it speeds up, it's going to have a change in kinetic energy. Think about that idea, because that's something that does pop up a whole bunch on particularly multiple choice questions on the College Board test. One last idea that I do want to mention that gets thrown in here is indeed the ideas of power. And power is the rate at which work is done. It's work over time. So when we talk about the ideas of power, power is measured in watts, work in joules, and time in seconds. So 1 watt is equal to 1 joule per second. We can use that relationship if we know the energy transfer, or if we know the work that's done over some time. We can find the power output. That's why you hear of machines and mechanical things being referred to the ideas of watt output, wattage. Even horsepower is, again, another term used to describe the power of something. It is simply the rate at which work is done. Within this unit, there's a bunch of different ideas. Please spend time reflecting upon them. Remember that energy is a scalar. The area underneath the force distance graph is indeed the work done. Mechanical energy is always conserved within a system. If there is energy lost, it's lost to other forms, particularly friction or other things going on. Think about systems and what you have going on. Draw things out, and remember, energy is a scalar. As always, thanks for watching.